Hello and welcome. In this video, we will be discussing the mechanism behind a nucleophilic acyl substitution reaction, a very common reaction in organic chemistry. Before we dive into the details of the mechanism, let's first observe our acyl halide, or an acyl group in general, our carbonyls. So if we take a look at this is an acyl halide because of this halogen attached here, and it is a carboxylic acid derivative because it closely resembles the structure of this molecule right here, as indicated by this. So now let's take a look and analyze this molecule. So as we can see here, we have a dipole that's formed as a result of this electronegative oxygen, if we recall from general chemistry, hogging the electrons away from this carbonyl carbon. And as a result, we create a partial negative charge on this oxygen and a partial positive charge by the carbonyl carbon. This carbonyl carbon is now considered electron deficient and therefore is very electrophilic in nature. And as a result, we will say that this compound is very reactive to nucleophilic attack. So, now that we've identified our electrophile, we have our nucleophile here, which is electron rich. And the main premise of a mechanism is to understand the relationship between the nucleophile and the electrophile, the electron rich species and the electron deficient species. So, where do you think this nucleophile is going to attack on this molecule? Pause the video and see if you have any ideas. When you're ready to come back, press play. Are you still with me? Excellent. Let's find out what happens. So, our nucleophile is going to attack our carbonyl carbon because it is very electron deficient, as we said before. Thus, the result of this breaks this pi bond, or this double bond, in between the carbon and oxygen, and those electrons are hogged back by oxygen. The result is a tetrahedral intermediate, and the reason why it's a tetrahedral, if we refer to our central carbon atom here, it's surrounded by 4 groups. The original geometry of the molecule was a trigonal planar, and the trigonal planar is much more stable than this tetrahedral intermediate. And therefore, it wants to reform that trigonal planar molecule. And the only way we can do that is by bringing these electrons down here to reform our pi bond, or our double bond, as we said before. And now, we have to kick something off. We have to remove one of our groups attached. Now the question is, which group gets kicked off? To determine this, we have to compare the pKa's of each potential leaving group here. So I will abbreviate this leaving group as Lg. Compare those pKa's. And the pKa's dictate how badly our substituents want to form a bond. So if we have a high pKa, it wants to very much so hold on to that bond. It does not want to break. Whereas a low pKa is indicative of a less stable bond, or in this case, it's a much weaker bond and it wants to leave. It's okay with being kicked off. So if we ranked our groups here, we would find that our carbon group, or our R group, has a higher pKa than our nucleophile if we're assuming it's less than our R group. And last but not least, our chlorine has the lowest pKa. So because we have the lower pKa here and the higher pKa here, which group wants to get kicked off? If you said the chlorine atom, you'd be correct. Now, the resulting structure is another carbonyl compound with our nucleophile substituted in place of our chloride. And that's the mechanism. Thanks for watching. Have a great day.